Hello. We're the VIP QUIP team, and we're presenting silicon photonics integrated circuits. I'm Yolanda, and
I'm Kyle Graham. Let's get straight into it.
introduction to PICs. They they enable low cost, small size, and high complexity solutions for many applications such as telecommunications, sensing, and quantum computing. And an important component in PICs are phase shifters. It allows one to control the relative phase of light in an on-chip waveguide. And for silicon PICs, phase shifters typically use the optic effect by which the um, reflective index reflective index modulation and therefore phase modulation is related to the temperature of the waveguide. And in this presentation, we'll be considering the following in this presentation. Different thermal optic heater architectures for silicon PICs, and we'll be comparing their thermal tuning efficiencies. Our target application is for arrays of thermally tunable microring resonators, where the resonance frequencies of each microring can be controlled by an in-ring thermal optic phase shifter. So our objective for this presentation is to test various ways to thermally tune waveguides and to produce predictable and desired phase shifts. Then we'll be using the concept of phase shifts paired with splitting the waveguides to design circuits with constructive or destructive interference based on the input signal and thermal injection. So the main simulation softwares we use are MATLAB mathematical simulations and ANSYS numerical FDE solver. So for thermal phase shifters, a metal slab is first inserted far above the waveguide, and then from there, power can be injected into the metal slab, and then the power from the slab spreads through the spreads heat through the waveguide, and then the heat will cause a phase shift of input signals, and then the phase shift and power are linear related, which you can see in the graph. And in the next slide, we'll show a bigger graph of it. So this is the graph that we got for thermal phase shifters. And then on the left, it's the wavelength versus the output intensity or input intensity. And then on the right, it's temperature versus output intensity and input intensity. And I'll hand it over to Kyle.
Okay, so the graph on the left, we basically got from making a waveguide with a wire up directly above it and then applying electricity through the wire to heat it up. And then it changes changes the phase of the waveguide. And as you can see in the x-axis is the power through the wire, and then the y-axis is the phase being changed from the heat. And then on the right is the heat distribution of the waveguide. And as you see in the middle, it gets pretty hot, and on the outside, it gets cooler. All right, next slide. All right, so the Mach Zedner interferometer. So essentially, it's a device used to measure small changes in the refractive index of a material. Um, when a small change in the refractive index occurs, it causes a phase shift in the light, resulting in a change in a pattern. And then you can measure the the pattern to uh basically measure small changes in the refractive index. Uh, it basically is a device that splits and recombines the light to create patterns. Um, and then as a result, the recombination of the light can cause destructive interference or constructive or different constructive interference. Um, yeah. Next slide. So destructive interference occurs when two or more light waves meet and their amplitudes are opposite in polarity, causing them to cancel out. And it can be optimized to filter out any unwanted signals or to retain signals in a certain range. Next slide. So in conclusion, our research points that optical circuits can be thermally tuned um, by these four different methods of inserting a metal slab above a waveguide via lithography, uh, power injected into the metal slab. The power causes heat to seep into the waveguide, and then the change in temperature causes phase shifts of the input signal. We also found that waveguide geometry, with the waveguide geometry, it can be altered to split the input signal into two branches and recombine later. Okay.